Sections 6.7 and 6.8 are about applications of exponential equations. So now we're going to be able to apply what we've learned about exponential equations to some real-world examples. Section 6.7 is all about financial models, in particular compounding interest. So we've seen this formula before. This is the simple interest formula, and it says if I have a principal, P dollars, and it is borrowed or deposited for a period of T years at an annual interest rate R, the equation for the interest rate charged is I equals P times R times T. Okay, so if I deposit money into my account, it's going to collect interest, right? And then what happens to that interest that I accrue? Well, I'd want to put it back into my account, and then the process starts all over again. I start to accumulate interest on my principal and the initial interest. This is called compound interest. And we don't just want to keep using this formula over and over. There's got to be a simpler way, and there is. So first thing I want to mention real quick is that there are different interest payment periods. So for example, interest could be paid annually, like once a year, or it could be charged annually, like in case of like a credit card. When they get a credit card, they tell you your annual interest rate, but they bill it monthly. The other way interest is billed could be biannually or semi-annually. Semi means half, right? So think like semicircle. It could also be quarterly, which is 4 times a year, or monthly, like your credit card, which is 12 times a year. I've never heard of daily interest before, but apparently it's a thing. Daily would be 365 times a year because there's 365 days in a year. However, some banks use a 360-day year. The reason for that is 360 is divisible by 12 really nicely, whereas 365 is not. So I put money in the bank, okay? At the end of the pay period, it accumulates interest, right? And I add that to my principal. It just is deposited back into your account. They don't send it someplace else. So that means that the interest computed on the next pay period, right, is going to be interest on your old principal plus the interest you earned on it the last pay period. We call this interest compounded, and compounded interest is interest paid on the principal and on previously earned interest. So if you're earning interest on interest, that's great because that's not money you put in. And if you have any questions about that, that's how 401ks work. You should probably talk to your parents and start one as soon as you can when you graduate in 3 to 4 years. So here's the compound interest formula. I'm going to go through it. You will be given it on the exam because I don't want you to have to memorize it. So the amount A after T years due on principal P invested at an annual interest rate R, notice that's your annual interest rate, expressed as a decimal, is compounded in times per year, is the formula. The amount equals your principal plus 1, right? That's what you initially had, plus your rate divided by the number of times it's compounded raised to the power of the number of times it's compounded times the number of years you left it in that account. So we call A our accumulated value. This is our principal and all the interest it's earned. P is the present value or the initial principal you put into your account. So why don't we go ahead and compare some compound interest. So let's say I were to invest $1,000 at an annual rate of 10%. What would the final amount in my account be after 1 year if I compounded, we're going to compare all these, annually, semi-annually, and quarterly? So for annual, I have my amount would be my principal P, which is 1,000, times 1 plus my interest rate of 0.10 over 1, right, which is my N. It's compounded once because it's annually, raised to the 1 times 1 because that's 1 year. That's my T. This would give me 1,000 times 1 plus 0.10, which is $1,100. So that's how much interest if it was compounded annually. Let's talk about semi-annually. That means I have A equals 1,000 times 1 plus 0.10 divided by 2 this time, because my n is 2, raised to the 2 times 1 power. So I have 1,000 times 1 plus 0.05 squared, and that would give me $1,102.50. Quarterly, my n is now 4, so I have 1,000 times 1 plus 0.10 divided by 4 to the 4th power times 1. Again, just following my compound interest formula. That gives me 1,000 times 1 plus 0.25. Yeah, 0.025 to the 4th, which gives me $1,103.81. So you would have thought, gut instinct, oh yeah, if I compound semi-annually or quarterly, I'm going to make a lot more than if I just compounded annually. It is a little bit more, not a ton, but that little bit can make a big difference, especially if you had way more than $1,000 invested. So let's go ahead and compare the amount we earned annually, semi-annually, and quarterly to the amount we would earn if we were compounding monthly or daily. So the amount if we compounded monthly would be 1,000, that's my principal, times 1 plus 0.10 divided by 12 to the 12 times 1. That gives me $1,104.71. So about 90 cents more than if I compounded quarterly. Let's go ahead and talk about daily. So the amount equals 1,000 times 1 plus 0.10 divided by 365, because my bank uses a 365-day year, to the 365 times 1. Remember, 1 is our T. That's our year. So I would get $1,105.16. That's if we compounded interest daily. Again, we're only making like 40 cents more than if we compounded monthly. Now, there's one other type of interest that we haven't talked about, and that is continuous compounding interest. So let's say the amount A after T years due to a principal P invested at an annual interest rate R is compounded continuously. So every second it's accumulating money. It's just compounded continuously and continuously. That formula is A equals P times E to the RT. So why don't we see how much more interest we would earn? So if I have A equals 1,000 times E, now I don't even need parentheses, that was a mistake, 1,000 times E to my rate, which is 0.10, times T, which is 1, I would earn $1,105.17 at the end of the year. This is only 1 cent more than if we compounded daily. And I thought that was pretty interesting because my gut instinct tells me oh yeah, continuous compounding, that's going to be so much more. Again, I did invest a tiny amount. I'm not rolling in it. But I imagine the more and more you do invest, that this makes a big difference. So why don't we work through an example? One thing I want us to know is that you can use the compounding interest formula to solve for the initial principal or present value. So we're going to use this formula to solve for P. What amount would I have needed to invest to get $3,500, so that's what I want in the end, after 7 years if it was invested at 3% and compounded semi-annually? Semi-annually means compounded twice a year. So I have 3,500, that's my A, equals P times 1 plus my rate of 0.03 over 2 to the 2 times 7 power. So I have 3,500 equals 1 P times 1.015 to the 14th power. That gives me 3,500 equals P times, I'm going to round this, 1.2316. So I need to divide both sides by this. And I get my initial principal would have been $2,841.47. Note, I'm always going to round to the hundreds place, especially because we're working with money. You can't get thousandths of a penny. You always need to round to the hundreds place. The last topic I'm going to talk about in this section is effective rate of interest. The effective rate of interest, denoted R sub E, of an investment earning an annual interest rate R is given by, if it's compounded n times a year, the formula R sub E equals 1 plus R divided by n to the nth power minus 1. And if it's continuously compounding, it's e to the R minus 1. So let's find the effective rate of interest given an annual rate of 5% compounded monthly. So then R sub E equals 1 plus my rate, which is 0.05, divided by n, which is 12, to the 12th power minus 1. I get 1.0512 minus 1, which is 0.0512. So it has an effective rate of 5.12%. Now let's find the effective rate if it was 5%, but it's compounded continuously. So now I need to use the formula with E. So R sub E equals e to the R minus 1. Well, that's e to the 0.05 minus 1. That gives me 1.0513. I wouldn't go any further than 4 decimal places. Minus 1 equals 0.0513. So 5.13% is our effective interest rate if we're compounding continuously.